Hello, class. So today, we're going to do something a little bit different from usual, and we're not going to be working directly off of the lecture notes. The reason for this is because the lecture notes are trying to show an interactive process for how to understand the relationship between the way that one is doing the coding to the actual mathematical results, right? And so, what I'm going to be showing today is essentially how do you optimize code in this mathematical setting with everything else around it, right? So technically what we did early in the course is all that you need to know, right? So you know everything about how to handle dynamic allocations, and you know everything about handling in-place mutation operators, and you know what PDE stencils are, um, you know about stiff ODE solvers, so technically you know everything. But in practice, using all the details together can be a little bit more difficult. So what I wanted to show in this course is something that could be useful for the final project, which is how do you understand the full performance of a code? How do you begin to put these ideas together and recognize where you need to make use of some of these tools? And how do you recognize when you think that you have it completed, right? So when do you take the stop and you say, I think that this is good? So here, for this exercise, I've obtained a code that is actually a generated code from a Python library that's trying to use the Julia differential equation solvers. And the question really was, can we optimize this code as much as possible, right? So this is a nice example that's showing up in practice from a battery modeling library. So from partial differential equation stencils. And what you can see in here is that, so what you can see is that this generates some vectors, right? So this is a constant vector. Here's a constant vector. Here is a sparse matrix. And so you can probably understand that, these sparse matrices, this has, minus 30 plus 30. This is a finite difference stencil of a partial differential equation. And so you can represent that as a sparse matrix, right? Which is exactly what we did explain in the course before. Um, Now, what I'm going to try to do is I'm going to keep the matrices intact. There's a way to be able to, unfold all the matrix operations, and that's quite a bit more work. But what I want to kind of show is, very very quickly just how to get a lot more performance out of this style of partial differential equation solver code. So here I've loaded everything into my RAM. I define a differential equation, which is just defined by these constant matrices and constant vectors. Um, there's an initial condition that's given, a time span, and when I run this with the CVOD BDF solver, I get a timing of about 2.6 milliseconds. Right. So the question is, can we do better? And to really answer that question, what we want to do is we want to turn to profiling tools. So what I'm going to show is the built-in profile for Juno, but generally all flame graph profile viewers are the same. So there's a package called profiledview.jl. There's nvprov, prof. There's a bunch of these different flame graph libraries, and not just in Julia. Flame graph libraries are used everywhere. So I'm going to just kind of showcase the workflow for how you get a flame graph and how you understand the results of it. So here what I'm going to do is I'm going to do using profile. So what a profiler it's a statistical mechanism that essentially takes account of where it is at predefined intervals. And so if you're running a code long enough, it'll take many counts from the parts of the code which are the most expensive, and it'll take fewer counts from the parts of the code that are less expensive. It doesn't necessarily give you an exact value for the amount of time spent in different portions, but it gives you a relative time that is fairly good. So what I'm going to do here is I'm going to say, well, this runs in 2 milliseconds, so that might not be enough time to run the profile. So I'm going to do a for loop over this, and I'm going to just run solve each time, and I'm going to app profile this. So I'm going to profile about 1 second of code, and hopefully that's enough. Um, So then what I'm going to do is I'm going to use Juno.profiler, right? And one key step here is that make sure that you've already gotten rid of the compilation before you run a profile. Otherwise, you'll see the compilation in your profile. It'll be a gigantic call stack, which is the actual compiler doing all this dynamic allocations. It's best to use, to refresh, you want to do profile.clear to be able to get a new clean profile, and then you just rerun it. That's a very nice way to get a new profile. And what we see here is then something called a flame graph. So if you look at what's up at the top right, so if you look at where my cursor is hiding right here, this is going to tell you all the information for what is the issue, or what is the area that we're going to be have to investigating. So here, this is the main program, not very informative line. Here, this is saying the top level scope is the profiling code itself. One level deeper is test at 2.jl, which is the file I'm working in, at line 223, which is this line right here. So it's saying that 100% of my time in the profile is in that line. That's good. That's what we expected, right? 100% of the time is in differential equation solves. That's good because all it's doing is solving. 100% of the time is here, and so we dig down, and when we get to here, it says that 100% of the time is spent in this line of code, which is doing the internal solve with the differential equation solver. But that's the last point where everything is all 100% of the time. Now there's some refined information. Um, so the relative amount of time is the relative size of the horizontal bar compared to the one next to it. So like 95% of the time is in the solver step. That's good, right? Because that means that the library itself is optimized enough that it's not taking most of the backend time. There is something in the library that is taking time. So if we look at this really quickly, it is in solve, in handle callbacks, in save values, in save values here. If you dig into this, what you see is that what this is doing is that this is defining the output arrays. So it's a little bit harder to dig into, but you can see that there's a similar call here. So that's an allocation creating a new array, because and then it's doing a interpolation to be able to save this output array. And so that's what this save values function does inside of the library. And so what we can see is that, for the way that we're solving the equation, so when we're solving it with this amount of save at, the amount of time that's actually done in the solver actually saving outputs is, you know roughly small amount of time. Um, so that's good to know, right? Because that is very application dependent. Let me change the value here to be something like 0015. I'll clear the profile, I run a new profile. This can actually take a significantly longer. And what we see here now is that the vast majority of the time is actually not in your solver code, but it's actually in the save values function, right? So this is a good way to understand that, if if this is what you see, that the 80% or 70% of the time isn't actually the code that you're running or the code that you wrote. It's actually just creating arrays and creating output. There's two things to do, right? One thing is to say, do I really need to save this many vectors? If you don't need to save that many vectors, if you can use a continuous interpolation that's provided by the library or something, then that is fine, right? But if you need a really refined time series for some reason, then this is the performance. The most that you could optimize your performance in this case is at least, you can turn, if you were to turn your amount of code into 0%, you can get about 30% faster. Um, that's so that's a way to be able to estimate the upper bound, or what we can call the speed of light, for what if your code was perfect, right? And that's above speed of light, right? Because technically your code shouldn't take zero amount of time. So that's a nice way to get an upper bound. And so you can see already that whether you should be doing certain optimizations are very dependent on not just the kind of code that you're seeing, but actually the application, right? Because here, just by wanting to save more points, it completely changes whether it's worth your time to optimize. So if we return this back, we see that with a much smaller amount of saving, then that is a much smaller, right? So This is more like what you would probably expect if you unless you're in the case of generating some extremely dense time series. So inside of these kind of scientific applications, they're all very similar. Optimization, nonlinear solving, solving ordinary differential equations. In all of these cases, you give the library an f function, and the vast majority of the time ends up being inside of the function that you give it. And the reason is because the libraries themselves are quite optimized, and what the actual code in the libraries are then trying to do after they're optimized is they try to call f as few times as possible. Right? So the library writer's job is to call your f function as little as possible. And your job is to make sure that this function that they're calling is as fast as possible. And that's how you get a very efficient differential equation solve, or a very efficient optimization run, or a very efficient nonlinear solve, right? So the algorithms is all about solving f as few times as possible using Newton-Krylov methods and everything that we discussed in this course. And everything else we discussed in the course is how do I actually write this f function fast enough so that way the library can call a faster version, right? And then those have compounding returns. So when we get to this point, right, we can see that almost all the time is inside of this solve call. And inside of the solve call, it's the solver step. In the solver step, it's running some cvode sum function, which is just calling f. Um, so this is actually a wrapper to a C++ library, which is going to be doing the actual calls to f for you. So basically, the C++ library is every once in a while saying, "Hey, I need to evaluate the ODE. Here I evaluate the ODE." And when it evaluates the ODE, it does this call. It calls Julia calls a C, which then says it needs to call to f. And then here we can see that it calls, this is the wrapper type that it gives, or it's then calling into this function f that the user gave. So here we go. This is the nice clear view of this f. Let me kind of clear this up a little bit. So here we can see that all this time is our f. And so all this time is us. That's probably not good. I mean, there's a little bit of profile or jiggle, right? So I would actually kind of think that it's not showing this as 100% of the time, but it pretty much probably is 100% of the time, actually in this line right here. So you can either look at it in two ways. You can either see it up here where it's showing me the the length of time spent on given lines by how far this goes into the line, right? So it means that this line takes more time than this line, or I can be looking at it down, right? So this line is 213, which is longer than slightly longer than 214. Either way, it's giving the same information, which is telling us that these two lines of code are really our big offenders. This line of code is not very significant, which means that 90% of our application time, right? Because if we look over here, the profile has actually duplicated this. So this function call is the same as this one. Sometimes the profile will realize they're the same and chunk them back together. Sometimes it doesn't. But essentially what this is saying is that this whole chunk of time is spending about this percentage of time on this line, percentage time on this line. And so essentially 60% of your code's time is here. 35% of your code's time is here. The rest for the 5% of the time is magical library stuff. So most of the time is in these two pieces. And so where in these two pieces is all the time? Well, so we can see that there's a long broadcast call. So this is doing some broadcasting, and now this is actually color coded, right? So when it's yellow, that means that there's some dynamic dispatch, which means there must be some um, code typing issues. And whenever there's a red, that means that there's garbage collection, which means that there must be something going wrong with the with the array up. It means it's creating allocations. So the first thing that we see is that we're hitting some very large dynamic dispatches everywhere. One reason to get dynamic dispatch everywhere is because you can't infer the types, and one reason you can't infer the types is because of global constants. So remember, this is something that we discussed, right? That, in right here at any time, I could change this to be, a big float, and it will still want to use the same compiled code, even though the number of digits in this constant changed, and so therefore it can't optimize as well. So what can we do? Well, so the solution here shows one of the ways to be able to do this, which is that we can enclose a constant. We can enclose one constant that has all of our constant values together, right? So um, what we describe in the lecture is that if you tell Julia, for example, that this is a compile time constant, then the library can optimize on this. Another thing that you can do is you can take all of these values and can enclose them into the function itself, so that way they are inferred inside of the function. Now you don't want to just naively move this inside of the function, right? Because if I do this, then this array allocation, this allocation of this array and all the matrix allocations, they will happen in every single call to F. So what can I do? Let me let me reverse this. Um, so what I can do is I can say here is going to be my constants. So let me cheat a little bit and see what I found to be the nicest way to do this. So here are my constants. So CS equals. I'm going to make this a big tuple. Yeah, so I'm going to use a named tuple for this object, where I'm going to say, if you haven't worked with a named tuple before, a named tuple is an object like x equals a equals 2, b equals 3. It's actually how keyword arguments are handled and interpreted internally in the libraries. So here, x equals a equals 2, b equals 3, and I can use x dot a, and this does the thing that. So instead of having a bunch of globals running around, I'm going to use a keyword, or I'm going to use a name tuple to be able to hold all these inside of a single object. So, um, so let's see. So I'm going to do, here is the name tuple first argument. Here is the name tuple second argument. Here's the name tuple's third argument. Here's the name tuple's fourth argument, right? So each of these things are now just going to be inside of this name tuple. It's going to be a pretty big name tuple, but it's going to make it much easier to handle the shipping of all these little tiny tools. So let's do this here, and this should build me one object. Let me try to figure out where I went wrong here. So let me cut this short and see if that. So if I cut that short, it's doing fine. And if I evaluate this in full, that is doing fine. So I think it's just that it's not auto-evaluating at all unless I tab all of these. So I'm just going to go and tab all these to make it easier on me to be running this. So here we go. Now we have a name tuple with all these subcomponents inside of it that's holding all of our data. Right. So now as I show um, in the answers here, I'm just going to put everything as some constant c inside of my function, and then I'm going to relabel everything with c. So let me do that part now. So I'm just going to do c dot, c dot, c dot, close the profile for now, dot, dot. This part's a little tedious. So, okay, so while I'm doing this, let me explain what the next step is. So now I need to use a closure to be able to put this value inside of the function, right? Because now I need to have C defined inside of the function, but I need to give the ODE solver the arguments that it wants, which is dyypt. Um, so how do I do that? Well, what I can do is I can define a overload, which is pybam of this equals pybam or f pybam of CS, right? So what I'm saying is grab this CS, right? This giant name tuple that I defined here, and make the 4 argument version be to take that and stick it inside of this function. And so the 4 argument version is this function where CS is hard coded inside. Now, if I use this, this is something that has, this is the 4 argument version that the ODE solver will use now, and it will now be something where everything is coming from this name tuple. Let's see how that works. Right, and so we chopped off quite a bit of time just by doing that process. Now let's kind of look at our profile again. And what we see in this profile, let me do more time so that way let me do a bit more time so that way it fills up the profile more. And that's not good. Um, every once in a while, there's a way so that you can actually cause a seg fault from overflowing the profiler. Yeah, it's not a huge deal. Let's just work through that by running it again. I'm gonna make this a little bit smaller. I think that the issue happens when you are doing that with libraries that do a lot of calls to C. So it's kind of you don't see it too much. It was something that existed pre Julia 1.0, but not something you see too often. But I think that if you call C libraries too much and you kind of try to stop them during their allocations, something weird seems to go on. So it's actually my fault in the sundials library. Yeah. So we'll just take a little bit for this to recompile and get us back going again. Okay, so there we go. We got another timing. So now let's run the profile. I made the profile a bit shorter so that way I don't hit that issue. Um, so here we go. Now we have another profile where we see that most of the time is in this call to your function, and then it's all inside of this function call, which is now calling into here, right? So it's calling into here, and then at that point, um, then it is doing most of the time in still in the same function, but definitely a significant less amount of time. Notice that it is labeling that this is a dynamic dispatch because once again we have a global, right, which is stuck into this function. Actually, if we try this out and we actually see add code typed, or warn type f underscore pybam. Let's do a du is similar to u0. So that way we have a du u0 e 0.0, right? So that way I'm just putting the initial conditions and stuff in here to see what the actual um, inference is like. And we see that it's not inferred, and the reason why it's not inferred is because this value is not inferred. So there's 2 things in here, right? So first of all, it's returning an any, which is because it's returning the result of this last line, which is something that we don't need to do, right? Because if we're just mutating, then it doesn't really matter what the return isn't actually used by anyone. So let's make the return go away. So that is something that kind of masks the actual issue. There's still a dynamic dispatch in here because of the CS. So what I show inside of the solutions here is I just say, let me make this be a constant. And that's the easiest way to handle this, to just make this high level with all of our constants, just make it be a constant value and the compiler will handle it perfectly. Another thing that you can do is you can use what's known as a let block. And when you use a let block, you can do let cs equal cs, and then you can actually have a inner scope where everything is inferred. And I think that this is a style that should work well. Um, so let me clear the profile again. So let me skip over this part for now. There is a way to make use of a let block to be able to efficiently stick this into here, but let me just do the constant form because that's just a little bit easier. So I'm going to take this, rerun it. I folded this code down because it's just a bunch of numbers, right? So, so okay, so let's revert that part a little bit, and we just say, instead of trying to use the let trick, which if you want to find it, you can find a lot of discourse discussion on using let blocks there. But here, if you have a standard set of constants, that's fine. If you have constants that you're generating from a function and you define these functions inside of a function, it's fine. So in most cases, using a constant or a function embedding is a good way to get inference. Um, so I myself almost never use the let block, but it's just kind of something to know about. But okay, let's see where we're at now. So now we're at about 1 millisecond, which is doing quite well in comparison to where we were. It's more than a 2 times speed up. Um, and let's actually look at the profile to make sure that we cleared up a lot of these dynamic allocation issues. Remember that each time you run B time, it's going to be pretty significant because it's doing many solves. So let me clear this up. Well, actually, this is all right over pro. Okay, so there's still a few um, issues that are going on at the lowest level because there's still some arrays being made, right? That's not good, right? So it's still flagging some garbage collection. So let's look at why there might be some arrays being created. So here we see that um, so here we see that we're doing the right thing with y, right? Remember that the difference between views and slicing is that views are non-allocating because they're pointing to the same piece of memory. Um, since we aren't actually changing y at all, then we might as well use views in each of these cases. But here we see that we have a a matrix multiplication between this matrix. So if we look at this, right, we have this matrix cs dot const, and we have this array right here. So that matrix vector multiplication is going to be allocating an output for what the result of the matrix vector multiplication is going to be. So this isn't what we want, right? So what we want to do is we want to use a function known as molbang, which is essentially um, it's inside of linear algebra. If you do using linear algebra, you do molbang, you'll see that there are some special calls to matrix multiplies that get rid of this extra allocation of the resulting vector. So here for you can see that there's a 3 argument format, which is the y(a)b goes to y, which is y equals a times b. So in another sense, molbang y(a)b, this is equivalent to y equals a times b. Right. So we want to use this instead of the direct multiply because this is going to have to be allocating the vector y, when if we really want to do this efficiently, when we look at this profile, we see that this array allocation is actually showing up as a pretty substantial portion of something that's going to be a large portion of our code time. So I do just want to note in passing that there's also a 3 argument form, or a 5 argument form that you can make use of, which is a times b, matrix multiply a times b times a scalar alpha plus a matrix c times a scalar beta. So you can actually make use of this to do a bit more optimization than what I'll be showing here. Um, that's left to the reader, right? So okay, so let's take a look at how to do this. So here is our matrix multiply. And so here what I want to do is I want to say that cache, you know, I want to make this into a mole bang of this into a cache one, right? But I don't really know, I need to actually have a cache one, right? So I need to have a mole bang, or if I do this, I need to have that this times at view of, I'm going to use u0 because that's defined on the outside here, u0 to 31. Right, I'm going to need a cache that is of size 29 elements. Let me actually put this into my CS here. I'm going to say that I have an extra cache one inside of here, which is a zeros of 29. Right. So that way, this is a c.cache one, which is where I'm going to store the result. And now once I have that result, I can, inside of the place where the matrix multiplication actually was occurring, I can put this c.cache one. Yeah. All right, but I can see that there's another matrix multiply here. And if you dig through the result here, you can see that, what I need to do is I need to be doing these, have a cache one, cache two, and kind of cascade down these matrix multipliers. So let's do this, right? Um, so here I'm going to look at, then if I do something like a CS, this matrix, and I just want a zeros of 29, just kind of know the output size. So this is giving me an output of size 31. So I'm going to need a cache 2. It's zeros of size 31. And so this matrix multiply is going to be replaced with, sorry, d dot cache 2. And that's going to be a mole bang of these guys into c dot cache 2. Right. And I think I might have created a parentheses issue. Nope, my parentheses are good. Let me remove some parentheses here. Okay, so now let me read the rest of the statement. It is a dot plus, a dot star, another star, so there's another matrix multiplication happening. So here's another way I like to do this. I want to take this whole portion. I want to then replace it for now. I'm going to say that x equals this whole thing right here at show x. Now I'm just going to do a call to f pybam of dyYP. Let me make this be CS2 now, just because I have a constant, so I'm going to be changing it around. CS2, and now I do U0 here, because that's defined nothing, and 0.0. Right? Um, du equals similar U0, just that way I have something to write the output to, and there we go. So this right, if I do this with a flush, I see that x is equal to this array. What I really wanted to show me is the size of x. So the size of x is going to be something that is size 31. Let's see, can I reuse my cache here? Yeah, so this is size 31 and this is size 31. And after that, I don't use cache dot two anymore. So I can actually make this be a c dot cache two dot equals, and then I can make this be c dot cache two. X is not fine. There we go. Let's actually put a time on this so that way we can see we still have 7 allocations going on in here. So what else do we have to do? Well, we have this matrix multiply, right? So let's actually look at the size of this output. So I have to show size of this output, which is going to be a size 30. So I do need another cache. So let me call this cache 3, 0, so 30. I'm being really lazy here with my constants. So this is a quick way to just kind of get things moving. So here I now have a cat CS3, throwing that in there. And now what I want to do is I want to make this be a mul bang into c.cache 3. And there we go. Now I have a c.cache 3 right here. And this is all a broadcast expression. So I can actually broadcast this in place back into the result. So now I'm down to 5 allocations, and this f function is running fairly fast now. Let me handle the next one. What you'll see is that this is actually almost a very this is essentially it's a system of PDEs where the two portions are the same size, and so we can actually do if you double check it, this is exactly the same matrix as over here, and so it's actually going to be able to use the same caches because after I've already used cache one here, I never reuse the value, so I don't need to save what's in there. So I can pull this out and I call this c.cache1 because I'm just going to overwrite the caches I already have. I'm going to do a mul bang c.cache1. And now from cache 1, what I have is, sorry, wait. Yeah, so then after cache 1, then I have this matrix multiply, which happens to be the same matrix as the one right there, right? So I can use the same cache as well because it has to be the same size. So this cache 2, mul bang of c.cache 2 here. Now I have, once again, a very long expression before the next matrix multiply. Figure out where the parenthesis ends there. It's going to be this whole expression. c.cache 2. Right, so I can reuse the same cache because I don't need the results in there once anymore, and so this is a free cache which is going to be the right size. You reuse there, and then this builds into a mul bang once more. This is a mul bang c.cache 3 between these two portions, and then this is going to be a c.cache 3. Right now, let's see where we're at. Cool, one allocation. Let's try to dig out where that is. Well, that allocation ends up being right here because here I'm creating an array from the broadcast and then placing into here instead of broadcasting it directly. Which, if you use your profiling tools, it would have pointed to that line as being. Let's actually do that. So if we do this, it says that there's one allocation left. And if we use our profiling tools, right, so we actually stick this into the integrator, we see that we should be doing a lot faster than before. So this is doing fairly well now. The allocation count is definitely much lower than before, but if we look at the profile, we still will find that there is half of the ODE allocating every single time. So this here, right? And it's saying that there's an array allocation here, and it's going to be from a. Oh, did I not clear my profile from before? I do want to make sure I clear, right? So do fresh new profile. So I do have my code all in here. Now inside of this line, I see that everything is kind of equally mixing between these lines now, except I do have this line, which is a much longer one with a matrix multiple or um, with an array allocation on the bottom. And that is going to be due to this last code on here. If I actually get a more refined profile, hopefully I don't segfault it. Let's see. If I get a more refined profile, I should be able to then have it isolate what line of code that was. So yeah, so now it's saying that where the red is with this line of code, which is right here, which is telling me that I missed a dot equals. So if I add this dot equals in now, to get this is a completely non-allocating function. It tells me that there's zero allocations. And so what this means is that, this is a fairly good form of the differential equation that I'm writing down and giving to the solver. So without changing the solver, I get this down to about 1 millisecond. Let me double check my answer key here and see that, yeah, that's about what I had seen before. So, okay. So that looks fairly good, right? So now we have this portion optimized. Um, Now remember that there's two parts to actually getting this correct, though, right? Um, Part of optimizing is this, the actual code optimization, actually making sure that we wrote down the algorithm in the best form. The second portion is to remember that you need to run the best algorithms you can. Right, so here we're doing all of our optimization on one kind of solver. If that solver is known to be quite optimized, that's kind of fine. But remember that you can have differences between solvers. Um, but let's actually take a look at this more. And let me get a window open here. Um, see my new tab. All right, so let's pull up the docs.diffeq.sciml.ai. Right, so what we're doing is we're doing ODE solving, and we see that in the ODE solver section, right, there's a whole bunch of different solvers, and what we went through in the course kind of covers a bit of how these kinds of solvers work. So these SDirt methods, these kind of more standard implicit ODE solvers. But let's go to the recommendations here and see, that for stiff problems at very high tolerances, it's recommended that you use Rosenbrock 2.3 or TRBDF2. At medium tolerances, if you have a small system, you might want to use Rodos 5, or you might want to use KenCarp. Right, so this is not the solvers that we're using. Let's actually see how much of a difference the different methods make here. Let's do using ordinary diffeq. So the methods that we want to look at are things like Rodos 5. We want to look at TRBDF2. We want to look at a KenCarp 4. We want to look at a new solver. So yeah, new stiff OD solvers are being invented in 2017, I think. So that's why this is KenCarp 4.7. Let's actually look at what this new solver does, right, from Kennedy and Carpenter. And what do I mean by new solver? I mean, if you look at this, sorry, let me look at my result here. So one of the things that we do need to be aware of here is that in order for this, so this actually intersects with something that we discussed in the course, right? That um, so what I'm seeing here is a forward diff dual tag issue, right? Which is showing up right here when it's trying to write into the when it's trying to write into the cache, right? So let me kind of describe where this comes from using our previous lecture notes. So if we go to the lecture on stiff ODE solvers, what you'll remember is that stiff ODE solving is all about doing these implicit equations, with Newton's method, and then solving the linear system that comes out of it, right? And what was described was that you need to calculate these Jacobians, but the way that you get these Jacobians isn't necessarily through just finite differencing, but also um, through automatic differentiation. And the lecture right before that was all about how automatic differentiation, or specifically forward mode automatic differentiation, is not necessarily is something that's done with dual numbers to be able to push forward all these derivative terms simultaneously to the way it does the calculation. So that's where we're seeing these dual numbers, right? So these dual numbers are showing up in the Jacobian calculation, the Jacobian of this function, so that way the stiff ODE solver can generate matrices. Why is this not happening from the C++ library? Well, because the C++ library doesn't have automatic differentiation in it, and so it doesn't have it as part of its default. But why would automatic differentiation fail here? Well, so what it's doing, right, is let's actually put a show statement in here at show type of y, and then we run this. What we see is that the array y is usually a floating point array, but every once in a while it becomes a dual number array, because this is when it does or this is when it's doing differentiation. Now, the way that I created the caches is incompatible with this, right? Because here I have a dual number, which means it has derivative values. This is a constant, and you can multiply dual numbers by constants, right? Just remember that that's equivalent to putting zeros on all the dual numbers. And so then I save the value in the cache, which is, I need to save a value plus all of its dual parts, all of its derivatives, but there is not necessarily anywhere to put that inside of the cache. Right, so this is only 29 numbers, whereas these dual numbers, they have all these derivative terms. Um, and so this is not actually enough memory to be able to hold the entire dual number, and so it errors. So what it's trying to do is it's telling you that it's trying to convert the dual number into a float 64, so that way it could put it into this array of float 64s, but it can't do that because, a dual number has n plus 1 many terms, which doesn't fit into the 64 bits that we have in this array. So what can we do? Well, the cheap way is to just say I'm going to do autodiff equals false. Right? And that's actually fine. So what this will make it do is it just says don't use internal automatic differentiation for the generation of the Jacobian code, because it's not using automatic differentiation. You only ever see arrays of floating point 64 numbers, and because of that, it's going to be not having this issue. And I should not have made it print out inside of the inside of that loop there, because that's going to take forever. It's spending more time printing right now than it is actually calculating. So I'm going to kill that with Control C. Oh, I forgot to run the code to get rid of the print statement. And now I'm going to run this again. Right, so this is one thing to kind of be aware of. Oh, actually, sorry, I had that window open. I'll make sure to re-show the error message there. Right, so Rodos 5 didn't actually turn out to be very good here for performance. The reason actually comes down to the size of the equations. So we discussed a lot about how Newton's methods are able to reuse Jacobians. this is not a Newton's method. It's a Rosenbrock method, which requires getting a new Jacobian at every single time because it's not doing an implicit solve. So it actually needs to exactly do the inverse. And so for very small equations where the O of n cubed operation is not too expensive, these Rosenbrock methods can get, they can be one of the most performant methods. But as the size of your system grows, um, it's no longer going to be viable. It's going to take more time than other methods because it's spending so much time. Um, because then it's spending so much time recreating Jacobians. And if you look at the documentation, it does explain exactly that fact, right? So this right here, it is going to explain here that and medium tolerances you use here and here, but the ODE solver that you use changes depending on size. And the reason why it changes depending on size is because this assumption that you can do a quasi-Newton method and reuse your Jacobian, so this is the non-reusing one, right? This is calculating a new Jacobian every step. Remember, in these lecture notes, we described how you can use one Jacobian for all your solves, which is true for most methods, but these Rosenbrock methods are doing something special, which doesn't allow that to happen, which makes them only optimize at small sizes. So, okay. Um, but let's look at before I get into how you handle those auto diff issues in more detail. Let's look at a few of these other methods. So I will say here that the automatic differentiation is not going to be as efficient as you might think it would be, right? And the reason is because forward mode automatic differentiation has the same time complexity as finite differencing, and so you don't generally get a massive performance difference from using forward mode automatic differentiation. It's more about its ability to um, be correct, right? So remember that there's this ability to have less numerical error. But we can see from the results here that we did find something that is, substantially faster than what we had with CVODE, and it's this TRBDF2 method, which takes the crown. I think that might actually be different from what I saw, a bit before, but this can be dependent on your computer and many other details. Here we see that there's a TRBDF2 method, which takes the crown and is about 5 times faster than the code that we started with after all these optimizations, right? And its main difference here is that it is calling F less often, and then now that paired with our faster F calls is, the champion. But let's figure out this last auto diff issue. So let's isolate this problem. And I describe this really quickly in the FAQ inside of the ODE solver portion. So if you want to find this in the future, you might want to go to the frequently asked questions in the differential equation solver, and you'll find this discussion inside of this portion down at the bottom about automatic differentiation and dual numbers, right? And there's this kind of cute thing I give here, which is all about something called a dual cache. But what I want to do is I want to derive the dual cache. So okay, let's so okay, so what's going wrong with this cache, right? The reason why we can't just naively use the method with automatic differentiation is because we have specifically defined a cache which only allows floating point numbers, and so when we try to write dual numbers into that cache, we get something that's incompatible, right? So we can't have this be something that is just floating point numbers. It also needs to be able to handle the case where you have dual numbers. So how do we do that? Well, let me actually dig into the source code of the library here. This is a kind of a nice little trick to kind of understand um, a few things are going on. So here what we can do is we can create something that we call a dual cache, right? So we can say that we have, instead of just a cache of the numbers, I can have a cache that has the array of numbers and the array of dual numbers. Let me pull this out here so that way. So here I can have a diff cache which has both of these values, right? And what I want to do then is I want to say get TMP of if X is a diff cache, um, and then I've taken a value Y, right? So what I want to do is I want to make it so that way I can do, you know, get my temporary variable, and I want to stick in here, cache one. So I want like hash one equals whatever comes out of here, but I want to give it my array y so that way I know when things are dual numbered or not, right? Um, so let me, yeah. So okay, so now I can say that when this is just a um, when the yeah when this is just kind of anything, what I want this to do is I want this to give me x.du, which is the non-dual portion, and whenever I see a dual number, so whenever I see a using for diff for this is a abstract array with um, for diff dual numbers inside of there, then I grab the dual version of it. Right? Because I need to have a big enough cache for my dual numbers. So now all I need to do is I need to make sure I build this diff cache instead of these with dual numbers inside of there. Right? So how do I do that? Well, there is kind of a trick that we need to know. Um, so if you look at these dual numbers, so let's actually pull one out. Let's actually do at show y of one or type of y of one inside of here. Right, so it's usually a float 64, but then it becomes a dual number where it has a tag on it, and then it says it's a float, and here it says 12, where that 12 means it has 12 partials. So it's taking 12 derivatives all simultaneously. Remember, so it's a size 13 number. The bit length is 13 because it has the primal term and it has 12 epsilons associated with it. But this first term is what's known as the tag. And the reason for the tag is because it makes sure that you don't add two dual numbers where the epsilons mean something different, right? So your epsilons for this differentiation, you might have a different differentiation that's going on where if you add the two epsilons, you might get something that makes no sense, which is called perturbation confusion, right? So if you're doing a differentiation with one code and that other code, you have another code that's calling it, that's simultaneously doing a differentiation. You can make your two perturbations hit each other and kind of collide, and then you can mix your derivatives, which you don't want. So that's known as perturbation confusion. And so there's a tag in front of these, so that way, if the tag is incorrect, so if you are trying to add two dual numbers that do not have the same tag, it will throw a perturbation confusion error telling you that you are likely doing something that is going to cause incorrect values, and so therefore it errors out. So we'll see that the naive way of doing this diff cache is actually going to fail because we're going to introduce a perturbation confusion. Um, so okay, so let's actually take a look at this, where what we want to do is, yeah, so I'm grabbing something kind of innocuous from the library here, which is let me explain this a little bit. So what I want to do is I want to say if I wanted to generate this, so let's say I had an array U that I wanted to build the cache for. If I instead want to build the cache for the version that has dual numbers associated with it, how would I do that? Well, what I would need to do is I need to know the array U that I'm starting with because I need to know the element type of the dual numbers. I need to know the length of it, and that's going to be known from the array type U. Let me get rid of this little detail. Is just all about making sure that it matches the same size. So that way, if this cache was a matrix, it kind of restructures back into a matrix. This is this is just library stuff. for handling extra details. But if we cut this down a little bit, um, what's going on here is that I'm saying that I want this to create a for diff dot dual of something with the same length as you. So, um, or what I'm doing here is I'm saying the tag is nothing. So, and the reason why is because this tag, right, when it's auto-generated, this tag has the function that is differentiating, so that way it can come up with a tag that's different in every single case, and therefore you can ensure that you aren't ever going to get perturbation confusion. It's hard to know in advance what that tag will be because I don't know it's going to show up inside of the U-Jacobian wrapper of the PyBand call of all this deep inside of there. And so what I'm going to do is I'm just going to make the tag be nothing. So what does this look like if I do a diff cache? So I'm cutting off a few of the library details here. So here I see that the chunk size is 12. I'm actually just going to hard code the chunk size. You can get what the default chunk size is going to be by actually asking for diff.pick chunk size given the length of the array. So here, for example, pick chunk size for a 32 length array and tells you it's going to choose 11 because that's going to be the maximum size. So actually this means that there's 12 numbers that are going to be inside of here where there are 11 epsilons, right? So yeah, let me actually just put that in here. Length of u. So here I'm saying generate a bunch of zeros, which are not 64 bits, but they're 12 times 64 bits because they're holding these dual numbers. And let's make a diff cache. This is where t for library reasons. So here, let me check this. I have a diff cache of zeros of 29, and I see that I have a thing with dual numbers. Where the dual numbers have a slightly different size than in the other case. I think that might just be due to, yeah, so let me, I do need to make sure that the duals are all correctly sized. And so I want to make sure that this diff cache comes from the size of u0. So I see. So this means that, yeah. So I need to make sure that the size of the duals is set to match the number of partials I'm going to get because we're differentiating by y, which is different from the number of duals you would get if you differentiated by c.cache1, right? Because those are different sized arrays. So what I'm actually going to do here is I'm going to make those two different ideas, right? So diff by array versus the array that I want to create a cache of. So I'm going to use the length of diff by to be able to get the size of the array for the chunk size or the number of partials. But then I'm going to use u to be able to tell me how big of a dual number I need to have, or how big of an array of dual numbers. So here we see then that let's see. Maybe I messed something up here. Oh, so I'm now hitting this. So what I'm seeing with the Stack Overflow is I defined a two argument function that's then calling itself repeatedly. That's not a good idea. So, but I know that this is going to be an array of dual numbers. So let me hard code this right here to be an array of floats of p4s. So you can start to see where some of these library styles come from. I think that now it's this up a little bit because I have another function hanging around. So let me avoid this cache, the Stack Overflow entirely. Right, so now this is exactly what I wanted, and this is going to be hopefully the right number of partials out of here. I think that the number of partials I'm getting is a bit off, but let me work through this a bit more. Okay, so what I can do then is I can say instead of having a value here, I can have a diff cache of this by u0. I can have a diff cache of this by u0. And then I can have a diff cache this by u0. And so therefore, let me now call this CS4. So you can see why you kind of want to keep things a bit non-constant when you're just kind of playing around with it. But here now I have this diff cache fully defined. And now remember, I can't grab the values directly. I want to use dispatch to grab these values. So I want to do a cache1 equals get tmp of cache1 c.cache1, and then I want to give it the thing to dispatch by. So I want to know whether I have dual numbers because of the term y, right? I want to do this with cache2, and I want to do this with cache3. And now whenever I see cache1, cache2, cache3, I need to make sure I use the diff cache tmp version. This should be good to go if I'm lucky here. Righto, so I did not define diff cache and overloads on 3, so let me do that now. So okay, let's see. What I'm missing is I put a diff cache 3 into. So this is saying I did a mole bang between an array, a sparse matrix, and a diff cache 3, which means I forgot to dereference 1 right here. And so now looks like it's something that's working. Now let me do this right here. And I see, oops, dimension mismatch. Inside of the Jacobian wrapper. And the reason why I'm getting that is probably because of the mismatch in the chunk size. So um, let me kind of ignore some of the extra library details and just kind of grab that chunk size again. Let me, just to make sure that this is correct, let me just hard code this in here for now. Still a dimension mismatch, so I think I might have changed the size of something. Let me see. So I have here at show this and at show size of here. Oh, this should be size of multiply. These are all the same size until it wants to get the cache 1 version, right? So what, and this is all the same size until I'm seeing dual numbers. So the something about the dual number size is actually incorrect here, which is that, see, oh, I need to make sure I use this build diff cache. Sorry. So now, oof, it cannot determine the order of the dual tags between this tag and nothing. Right, so this is what I was mentioning about the fact that it's saying that I have a potential perturbation confusion because I have different tags. But the tags here, like notice that I've done this so that way I have exactly the right size of the underlying values. I just have a difference in the types. And I kind of want to masquerade my type to act like it had this tag. So what I'm going to do is I'm going to use something called Reinterpret, where Reinterpret allows me to change the type interpretation of a block of memory. Right? So I'm going to say that this block of memory, which corresponds to a dual of this many things, make it act like this dual number, which has all of which has the correct tag on there. So what I'm going to do here is I'm going to say Reinterpret this as an array of um, or reinterpret this as a type of y. I want this array of dual numbers to get exactly the tag of this one, and that's what I want to be returning from that's what I want to return from getTMP. I think that maybe I need to be doing the element type instead. Yeah, so I need to do the element type. So I need to say make the elements be something that has this tag. So very similar. And there you go. Now you see that automatic differentiation is working on it. And the whole thing is making sure that you understand the way that you're building your caches has to be compatible with the dual numbers, and this gives you then the optimal combination. Let's actually see where we ended up. Oh, it's going to be slower if it's printing all that. Let's get rid of the prints and go. Yeah, there we go. Didn't look like, again, I don't always expect forward mode automatic differentiation to help. Actually, it looks like here it didn't end up as optimal. The reason why is we can dig down, see what kind of SIMD it's generating. Is it generating as good SIMD as the forward difference code? There's a lot to kind of dig into here. But I think that I'll be leaving this profiling at this point, and just kind of saying that. So okay, so there's right there. Here you can see the type inference compilation call. Oh, that's because this is with this other ODE solver. So you can see that there's a lot more going on when we have um, the the there's a lot more going on when we have all this materializing with these sparse matrices and everything with the chunked partial. So you can see this is all hitting the sparse diff tools code where it's doing forward mode automatic differentiation. But it turns out that this forward mode automatic differentiation doesn't seem to be as efficient in this case as the has the finite differencing, and there's many reasons why that could be the case. So we can turn it off for now, but in some cases it's the other way around. It really depends on a lot about the application. Yeah, I think that'll leave it that for now because you can now see how, oh, if you want to understand why forward monomic differentiation is slower than this case, well, you can look at the profile for the AD code versus the non-AD code and start to signal out what are some of the issues, try to find out if they're algorithmic, and it's the same process all the way down. But hopefully this ties together a lot of the details of the course for how you understand automatic differentiation and its relationship to code profiling and code optimization and start to tie together all of these different ideas.